Good morning, or I guess good afternoon or good evening, or whenever you're tuning in to join me in Geometry A. This is Mrs. Brunk. So today we're going to continue on the same theme of yesterday's lesson of using a slope criteria to prove some quadrilaterals, or certain kinds of quadrilaterals. Like yesterday we proved that figures were parallelograms or trapezoids by showing that they had either one or two pair of parallel sides. Today we're going to kind of look at some of the other quadrilaterals that have perpendicular parts, so whether they're perpendicular sides or perpendicular diagonals. And we're going to use that slope criteria to prove perpendicular lines. So our learning goal is to prove sides of quadrilaterals are perpendicular using the slope formula. And we're going to be able to find and prove what quadrilateral is formed by four linear equations. Okay. That's our other learning goal, our second learning goal. So the theorem, the slope criteria for perpendicular lines, and this is something we've talked about already this trimester, back when we studied parallel and perpendicular lines, and we learned that two non-vertical lines are perpendicular, okay, perpendicular, if and only if the product of their slopes is -1. Now, another way to say that is that they are opposite and reciprocal slopes. So, opposite and reciprocal, that's about as completely different as you can possibly be. So these slopes are about as opposite as they can be, and that's why they're forming 90-degree angles. Because if you take two lines that are parallel and you take one of them and you turn it to the complete opposite direction, you will make a perpendicular or a 90-degree angle, right? And so you're changing that slope as much as you possibly can. So opposite and reciprocal. Here are some examples of some opposite and reciprocal slopes. So say the first line has a slope of 3/4. The line perpendicular to it would have the slope of -4/3. So again, reciprocal, where if it's written as a fraction, we can flip it. So if it's not written as a fraction, write it as a fraction, and then change the sign. So it's opposite and reciprocal. Here's another pair. So there's the first pair. There's another pair, -4 and +1/4. So the theorem actually said that their product of their slopes is -1, and if you take either of these pairs and you multiply them, you'll get -1. So like, for instance, -4 times 1/4 would equal -1, right? So that's where that criteria comes from. But it's the functional part of the theorem would be to say opposite and reciprocal slopes. So it's easier to identify when we define it that way. So let's go ahead and take a look at some figures and see if we can use the slope criteria. So if we want to show that the figure A, B, C, D in this graph is a rectangle, remember that rectangles have 90-degree angles. And actually, remember, we actually learned that if you have a parallelogram, okay, that if it has at least one, or if you can find that it has one right angle, then that guarantees that all the angles are right angles. So one approach to this would be to show that opposite sides were parallel. So to show this is the parallelogram. And then you could show that one of the angles was 90 degrees by showing one of the pairs was perpendicular. But since we've got to calculate the slope, we might as well just kind of dig right in and find the slopes of all of these sides. And then we'll kind of take a look at that criteria and see if we've met it to prove that all these angles are right angles. So since there's a lot of slopes to calculate here, probably using the counting, the rise and run. You know, remember slope is rise over run. Oh, and just real quick, if I haven't reminded you in a while, my dogs are snoring, and I'm sure you can hear them in the background, so hopefully they're not too loud that it's distracting. But anyway, we're going to find the slope of AB, BC, CD, and then AD. So all the sides, we're going to just take a look at all of their slopes and see if we can establish that the sides that are next to each other, the consecutive sides, are perpendicular. So we'll start with AB. So in AB, in order to get from A to B, you'd have to, let's see, go up 1, 2, 3. So you'd rise 3, and you'd run 1, 2, 3, 4, 5, 6. So the rise is 3, and the run is 6. That reduces to 1/2. So that's my slope. So now we're going to go over here and we're going to do the BC. So BC, to go from B to C, you'd have to go right 1, so that's +1, and you'd have to go down 2, so that's -2 for your rise. So here the rise is -2, and the run is 1. So that's a slope of -2. Let's see, CD, so to go from D to C, I usually just start on the left, like the point that's furthest to the left, and go to the right. So, I mean, but you could also go from C back to D. It's up to you. So from D, I'd have to go up 1, 2, 3. So I'd go up 3, right? Oops, I'm going to put that in a different spot. I'll put that on this side. Up 3, +3, and then 1, 2, 3, 4, 5, 6. 6 to the right. So you can see that mirroring what we did up on AB, right? So the rise was 3, the run was 6, the slope is 1/2. And then finally AD, so I'm going to do another color here. So this one, I'm going to go from A to D, I'd have to go down 2 and right 1. And so the rise is -2 and the run is 1, which makes the slope -2. So what we have is we could establish that this is a parallelogram already. We know that these opposites, we have these opposite sides have the same slope, right? These two sides are -2 and the other two are 1/2, right? But what we're trying to do for a rectangle is we're trying to prove that this consecutive sides are opposite reciprocals. So if you look at that, the pairings here, the ones that are next to each other, they're opposite reciprocals, right? And then we got the next pair. These are opposite reciprocals, right? Oops, and I didn't finish writing this out. And then these are, we got another pair of opposite reciprocals here. The next pair next to each other. And then, of course, going back to the beginning, we've got this pair is also, they're all opposite reciprocals. So they're all the consecutive sides. You could say like consecutive. You abbreviate that, sides are perpendicular. So 4 right angles. Because perpendicular lines make 90-degree angles. So since we have 4 right angles, it's a rectangle. So we've just shown that it is a rectangle by showing that all of the consecutive sides are perpendicular. Okay, so now in this next figure, they want us to prove that this is a trapezoid with 2 right angles. Okay, so the right angles that are most likely going to be, clearly are going to have to be K and L. So we'd have to be able to show that the sides that are next to each other that make these angles are perpendicular. But we also have to prove that this is a trapezoid. So not only do we have to prove those are 2 right angles, but we also have to prove that JK and ML are parallel. So really, it's just probably the easiest thing to do is just to go ahead and calculate the slope of the sides, except for we don't really need to know about JM. JM's clearly not parallel or perpendicular to any of those other sides. But we want to prove that this pair of sides is parallel so that it's a trapezoid. And then we want to prove that these little angles right here are 90 degrees, right? So let's go ahead and calculate those slopes. And then we can come back and kind of process all that. So let's look at JK, its slope. Then we'll look at KL, its slope. And then we'll look at ML, find its slope. And then we can kind of process this to make sure we've verified that we have a pair of parallel sides and we have these two right angles there. So let's see JK. And again, I like to start at the left when I count slope and I go to the right. So let's see, that's 1, 2, 3, 4, 5, 6. I'd go 6 to the right and 1, 2 down. So the rise is the down part, so that's -2, and the run is 6. So that reduces down to -1/3. Now I'm going to go ahead and I'm going to do the one across from it in the ML, make sure that they're parallel, and then we can look at JK, or I'm sorry, KL. So ML, to go from M to L, I have to go down 1, and then 1, 2, 3 to the right. So my rise is -1, and my run is 3. So there we go. We've got that parallel pair of sides. And now we're going to look at LK. So to go from L to K, I'm going to go to the right 1. So I'm going to add 1, and I have to go up 1, 2, 3. So up 3. So the rise is 3, the run is 1, the slope is 3. Okay? So we've got this pair of sides. They're parallel, so we got the parallel sides, right? So so it's a trapezoid. And and oh my gosh, my dogs are in full force right now. So then this pair and this pair, those are opposite reciprocals, and that means that, so since these are, and then 2, those are both perpendicular, JK and is perpendicular to KL, and ML is perpendicular to KL. So K and L are right angles. Okay, so make sure you get those descriptions in there too. They just kind of help you to process what you found here. So it's really not necessary to find the slope of the side JM because it really didn't have anything to do with what we were trying to prove here. So, okay, so here's one that we're going to designate as a you-try question, right? Because this is one that's just like A. You're going to establish that this is a rectangle. So I just want you to pause the video and find the slopes of all 4 of those sides so that you can make sure that the consecutive sides meet the criteria for being perpendicular lines. So again, what you're going to do is you're going to want to list every one of these out. DG, DE, EF, and GF, or FG, doesn't matter how you call them, but anyway, and then find their slopes so that you can establish that you have consecutive sides that are perpendicular. So pause the video now. So thanks for giving that a try, and you can see from the calculations that you've got your opposite sides are parallel, but more importantly, what we're trying to show is that the consecutive sides, the sides that are next to each other, each pair of consecutive sides is their opposite reciprocal. So all consecutive sides, so you could say something like this, consecutive, which means next to, right? Sides are all perpendicular. And then the reason why is because they have opposite reciprocal slopes. So I did not mention or do this method, but remember you can always calculate the slope by using the coordinates, but you just kind of imagine what a task that would be on these because of just, you know, like the sheer confusion of all the coordinates and substituting in the slope formulas and then possibly making sign errors. And So, you know, when you have it graphed like this, just counting the slope is really your best bet. So now in our final examples, we're going to be looking at graphing some lines and seeing what kind of quadrilateral is formed by the lines. So I know in your notes you have quite a space between the graphs and these tables, and you'll see why in a minute. But just so that these could be on the same page of my notes, I just shortened up the spacing there. But so we may have to kind of do some erasing to fit everything in. But so the first thing we need to do is we're going to have to graph these lines that we see here. So in order to graph lines, our easiest thing to do is to put them in slope-intercept form. So that's the first thing I'm going to do is take, and this is why there's so much space here. So if I took Pine Street, okay, Pine, and I put that equation into slope-intercept form. In order to do that, so I'm going to, you can write these out, and then I'm going to erase them and just rewrite the answer, but since you have space, you can just leave it on your paper. But so the first thing I'm going to do is I'm going to take this, I got to solve for y, right? So I'm going to take this x and bring it over to the other side. So that'll say 2y equals x plus 4. And then I'm going to divide by 2. Everything gets divided by 2, right? So that leaves me with y equals, and then since there's not anything really in front of the x, what that means is there's really a 1 there. So that's really 1/2 x, and then 4 divided by 2 is 2. So that is line P, which is Pine Street, and we can go down here and graph that. That's Pine Street. Okay. And graphing, when it's in slope-intercept form, remember all we have to do is plot the y-intercept, so that's 2. And then we just rise and run according to the slope. So the slope is 1/2, so we're going to rise 1 and run 2. And that puts us right here. And if I connect those with a line, it's going to look like this. Okay, so that's my first line, and that's line P. Okay, so now I'm going to do the exact same thing, but we're going to do that with Elm Road, and we're going to do it with the Chestnut and Cedar Road. Okay, so Elm Road is going to be pretty easy to put into slope-intercept form. All I have to do is take the 2x to the other side. So Elm Road, when I bring that 2x over to the other side, it changes the sign because I'm going to subtract 2x, right? So that would be y equals negative 2x plus 7. So I'm going to graph that one. So that one has a y-intercept of 7. Ooh, and that's not going to be good because how we're going to fit that on there is going to be interesting. So let's see, I'm going to have to extend this out. Hold on. We're going to extend out our axis a little bit and see if we can fit this on. So you'll have to kind of extend that out a little bit. It only goes up to 5. But that's okay. We can make do. Now I'm going to just add a couple tick marks. So that goes up to 5, then 6, then there's 7. So approximately 7. So we'll put the y-intercept right there at 7. Okay, and then the slope is negative 2. So that means go down 2 and right 1, down 2 and right 1, and down 2 and right 1. And then all we have to do is connect those, and we get our line right there. Okay, so we got 2 lines now, and now we're gonna get the other 2. So I'm gonna keep changing colors. It just kind of helps stay focused on which one we're graphing. So actually, that one was Elm Street, so I'm gonna label that as E right up here. Okay. Ooh, not there. Maybe I'll do it down here because there we go. So the next one, I'm going to pick green. We'll do it in green. So that's Chestnut Street. So Chestnut Street, all we have to do to get it in slope-intercept form is now divide by 2. So if I divide the 2y by 2, I just get y. And then if I divide the x by 2, that's actually 1/2 x. And then the minus 6 divided by 2 is minus 3. Okay, so that one I'm going to graph. That's got a y-intercept of negative 3, so I plot the point on the y-axis at negative 3. Then the slope is 1/2, so I'm going to rise 1 and run 2. Rise 1 and run 2. And then I'm going to draw the line that goes through those points. And then I'm going to label it as, that is Elm Street. Oop, that's Chestnut. Sorry, that was a Chestnut, that was a C. So Chestnut Street. And then, let's see, final one is Cedar Road. So all I have to do to get that one in slope-intercept form is to simply move the 8 to the other side by subtracting it. So Cedar Road, that's another C, would be y is equal to negative 2x and then minus 8. Oh no. That's definitely not going to fit on there. So now that's going to be a y-intercept of negative 8 and a slope of negative 2. So we can't fit that one on there. So let's see if I could just pick a couple points to plug in there for that one. So when we can't fit that on there, that's okay. We can just plug in x values and then figure out the y's. So let's say I plugged in negative 2. Okay, so if I plug in negative 2 in for x, let's see, negative 2, that would be negative 2 times negative 2. Then plug in negative 2 for x, minus 8. So that would be actually positive 4 minus 8, which is negative 4. So it would be negative 2, negative 4 would be on this graph. And then let's say I plugged in negative 4. So that would be negative 2 times negative 4 minus 8. So that would be 8, positive 8 minus 8, which is 0. So now we'll just put in 0 there. So now we got some points to graph. So negative 2, negative 4, 1, 2, 3, 4. And then negative 4, 0. So yeah, that graph is going to hit down way too far. We weren't going to be able to fit that on there. So that's okay. You can always plot points to graph a line. And to connect these, now it looks like I need to make my one line a little bit longer. My blue line didn't get, that's why I always want to try to make sure you extend them way out all the way across. So what does this look like? Well, this looks to me like a rectangle that's, got 90-degree angles. Now, how do I know for sure? Well, look at the equations. Well, remember, we just put these in slope-intercept form. So we can just look at the slopes of the lines in the equation. So like, see, there's 1/2 and then negative 2. Those are next to each other. And here's 1/2 and negative 2. Notice how the slopes are all opposite reciprocals? So that means this must be a rectangle. So it's a rectangle because we've got all consecutive sides are 90 degrees. They're all perpendicular. So yeah, that involves quite a bit of work to put those in slope-intercept form and graph them, but it's great practice. So we'll do one more together, and we won't have one that's designated as necessarily you try, because this is kind of a skill we've got to make sure we review really well. So let's see, the first one, Clay Avenue. If I'm going to put this in slope-intercept form, I'm going to have to add the 9 to both sides. So let's see, this will be Clay Avenue. And I'm going to add the 9 to both sides, so that makes 3y equals x plus 9. And then we divide by 3. So if we divide everything by 3, that's going to make Clay Avenue be the equation y equals, well, there's only a 1 in front of the x, so that's 1/3 x, and then reduce the 9/3 to 3. So that's Clay Avenue. So let's see, put that on the graph. That's going to be a y-intercept of 3, a slope of 1/3. So that means rise 1, run 3. I could also go down 1 and left 3, and that would give me that point. So that way I make sure I get my line long enough this time. Oops. And so there's my line. And then that's Clay Avenue. Oops. And then, let's see, so Fresno, that one's pretty easy to put in slope-intercept form, because all I have to do that is to take this 2x and subtract it from both sides. So if I bring it to the other side, it'll be subtracting 2x, so that'll be y equals negative 2x plus 3. So let's see, plot that point at positive 3, and then slopes of negative 2. So go down 2 and right 1, down 2 and right 1, down 2 and right 1, and then all I got to do is connect those. And let's see, so if I connect those, oops. I didn't do a very good job. Okay. Let me try that one more time. There we go. That's better. Well, that definitely does not look like a 90-degree angle, and I know it's not because those slopes are 1/3 and the other one is -2, so they're not. Ward Street, in order to get Ward Street in slope-intercept form, I just have to divide everything by 3. So that's going to actually be, let's see, I just made a mess of that equation now. So if I divided everything by 3, it would be, oops, y equals, oh, shoot, 1/3 x minus 5/3. Ooh, okay, so that one's really not nice. So that's a negative 5/3 y-intercept, so that's 1 2/3. So negative 1 2/3 would be right about here, and then it's a slope of 1/3. So you're going to rise 1, so that's a full one right there, and run 3, 1, 2, 3. Puts us right here, and then connect, and there we go. Well, at least I can tell that these opposite sides here are, see these two right here are parallel. So I know that these are parallel sides because they have the same slope. So I at least have a trapezoid, but then we got a final one to find out. So the last one, again, I got to put it in slope-intercept form, but all I have to do that is bring that 4 to the other side. So that's y equals negative 2x minus 4, because I have to subtract the 4 to get it to the other side, right? So now I'm going to plot that. That y-intercept is negative 4. The slope is negative 2. So that means I'd go down 2 and right 1, but that would be kind of hard to fit in. So instead, you could also go up 2 and then make the run negative, so left 1. So up 2 and left 1, up 2 and left 1 would put me right there. Connect those, and oops, I didn't do a very good job of getting those points. That's not good either. There you go. And what I can tell right now is that these two lines are also parallel. See how they're both -2 slope? So we have both pair of opposite sides are parallel, and that means we have a parallelogram. So when they ask us to tell what kind of quadrilateral this is a parallelogram. All right, so that was a really good review of putting in slope-intercept form and graphing as well, and then using the idea of slope to classify a quadrilateral. And that does it for today's lesson. Thanks for coming to class.